So ice boxes. So let's consider an example we talked about yesterday. We're going to have hydrogen gas reacting with nitrogen gas, and we're going to produce ammonia gas, NH3. And what I'd like you guys to do right now is I want you guys to write the equilibrium expression for this. So go ahead and write that equilibrium expression. Remember that starts with K, EQ. I'll let you guys take it from there. So go ahead and start writing that expression down. It's a good thing to practice. That's NH3. NH3 is ammonia. Okay, so if you guys recall, what goes on top?
The product.
Yeah, product goes on top. Product goes on top, and we raise that to the power, the power of our coefficient. On the bottom, we're going to have our H2 to the third power and N2, no exponent. Okay, so that's the same as yesterday. So you're going to start off, that's your first step for these problems. Now, the issue with these problems is what happens if we don't have the reaction at equilibrium yet? How can we figure out the equilibrium expression?
With the arrows?
We're actually going to use the arrows, yeah. And I'll show you in just a second how we get to it. So we're going to say, in this scenario, that we're going to add 0.50 moles of H2 and same amount, 0.50 moles of N2 into a 1 liter flask. So basically, I've got my little flask right here, and pull H2 in there, pull N2. And then we're going to let it react. And then when we get to equilibrium, after it sits for a while, we measure the concentration of ammonia, NH3, and it's found to be 0.20 molarity. And we want to find what the equilibrium constant is for this. So this looked pretty similar to stuff yesterday, right? The way you can tell that it's not going to be the same is that we aren't starting at equilibrium here. We're actually starting where we have none of the ammonia present at all, so it hasn't reached equilibrium yet. We don't know what the concentrations of these guys are at equilibrium, so we have to figure that out before we can calculate the constant. And how we're going to figure that out is we're going to use this method called the ICE method. And what the ICE stands for is initial, change, and equilibrium. And with this, we're going to make a little box. It's called the ICE box. And what the first thing you do is put the letters ICE down like a left-hand column. Then across the top of the ICE box, you are going to write the equation for this reaction. So you're going to rewrite that. And with my ice boxes, I always err on the side of being a little bigger, leaving myself room to kind of write my numbers in nice and big. So here's my ice box. Yeah, it's a table. Ice table doesn't sound as cool, though.
Oh, sound right.
Yeah, that's right. That's right. Okay. Now, what you can do is we can start entering the information we know about this equation. So, what do we know? Do we know the initial concentration of hydrogen?
3.
Was it?
The concentration.
Yeah, it's 0.5. It's 0.5 because we got 0.5 moles in 1 liter. So even though there's moles here and liters here, remember that moles over liters, so it's still going to just be 0.5. So we have 0.50 molarity hydrogen. The same deal for the nitrogen. We initially just added it. We have 0.50 molarity nitrogen, right when we initially added. How much ammonia do I have at the start of this reaction? How much? We don't know. In a way, we kind of do though. So I just have nitrogen, hydrogen, put them together, and that exact moment, how much ammonia is there?
1.
None.
Oh.
There's no ammonia. The reaction hasn't started yet. So initially, there's no ammonia. We do know that at equilibrium, we have 0.20 molarity. So we can put that in for the equilibrium. Okay, so we got that information. The next thing I like to do is I put some arrows in. I put actually in those arrows that we did in the Chateliers, because we're essentially affecting equilibrium at the start of this reaction. So when we go from initially to equilibrium, what's going to happen to the concentration of hydrogen and nitrogen? It's going to go down. Yeah, it's going to be lower than it is initially. And then what happened to the ammonia concentration? It goes up. So yeah, put those in. What effect's going to be from the reaction? Okay, and this is important to put those arrows in for a reason. We say that the concentration and these things changes by a factor of x. So we know that by some factor, the concentration is changing in all of these. And that's like kind of derived from the equilibrium constant. So in this one, we say that it changes by a factor of plus 2x. Why plus? Because it's increasing. And then the factor is unknown, so we call it x. And they're all changing by that same factor. Where do the 2? The 2 comes from the coefficient, and the plus comes from the arrow. So that's where that 2, and that's where that plus comes from. That was really poor arrow design right there. So yeah, the plus comes from the arrow, and the 2 comes from the coefficient. Thanks for humoring me. So what is it going to be in this case? What do we call it? Yeah, minus 1x. So it's just from the coefficient. And then the arrow sign. And then this one? Minus 3x. So now check this out. We have all of the information for one of these to figure out what x is. And then because we just have one unknown in these guys, once we figure out what x is, we can figure out their equilibrium concentrations. So here we initially have 0. We add to it 2x, and that gives us 0.20 molarity. So now we just have to solve for x. So this one, yeah, we can just subtract 0. So that just goes away, right? So that just goes away because don't have to worry about 0. And then how do we get x by itself now? You divide by 2. Divide both sides by 2. And x equals, 0.1 molarity. That's the factors everything's going to change by 0.10 molarity. Now we can go back to these ones, and we can plug X in to figure out what their equilibrium concentrations are. So we know that N2 initially starts out at 0.50 molarity. We subtract it 1x, or 1 times 0.10, and that's going to equal our equilibrium concentration. So what's our equilibrium concentration for N2? 0.4. Yeah, 0.40. And we do the same thing over here. We initially have 0.50 molarity. We subtract from it 3x. And we get 0.20 molarity. And that's kind of what, you notice how I drew the icebox kind of big? Just to leave myself room below to calculate. So that's why you make the icebox so big. Okay, now we have enough information to find the equilibrium constant. We need to have all these concentrations at equilibrium to figure this out. So now we can take that stuff and plug those numbers in to figure out our equilibrium constant. So we'll use that initial equilibrium expression we developed up here to get it. So what's going to go up top? Our product. And how much of the product we have? 0.20 molarity. And we're going to raise that to the second power. And then we'll enter information below. So we've got hydrogen, also 0.20 molarity. And we're going to raise it up to the third power. Then our nitrogen, bless you, we'll do that to the 0.4, or not 0.4, 2.4. We'll multiply by 0.4 molarity. And again, I would like you guys to practice, run it through your calculator. Just practice those order of operations on these ones. What I suggest then, too, if you still can't get it right, just put in the calculator. What I want you to do is kind of like first calculate 0.20 to the second power and then rewrite it.
Okay.
Okay? So do those, do your exponents, do all multiplication you need to do, and then do your division last.
Should you get 0.04?
As a final answer on this one?
No. Like,
oh, on this first part? Yeah. I'll tell you, too, that since all these numbers have 2 sig figs in them, our final answer will as well. And you guys get it? So we're on it? Yes?
I got 2.
I'll have you retype her in. This is good. This is good. That's good. We got to figure this out, so that way you're all set on Monday for these.
12.5?
12.5? Yeah, so it's 12.5, and that's a 13 with 2 sig figs. One more question. This doesn't come up on the questions at all, but I like to just ask it because I think it's important for you guys to know. Product, reactant favored? Neither?
It's
Product favored, yeah. Product favored because it's bigger than 1.
Still didn't get it.
We can work on that. We can work on that afterwards. Yeah. So yeah, that's product favored. So let's do one more, and then because there's a little nuance that shows up in the next one, and then I'll turn you guys loose on this. Give you some time. Okay. So the next one's going to be a little more generic. You'll see what I mean. We're going to take 3A and combine it with B. to make 2C. It's all in the gas state too.
If it's a solid, it's just like take out of the equation.
Yeah, if it's a solid, we just won't even include it. Consider it a 1 or don't even include it. So let me give you the scenario on this one. We add 0.40 moles of A and 1.5 moles of C into a 2-liter flask. We allow it to get to equilibrium. So at equilibrium, there are 0.40 moles of B. And again, we're just going to find K on this. On these ones, I'm only going to have you guys find K. Okay. When you guys get done writing it down, I see some of you are already doing this. The first thing we always do in these is...
Hold on. First thing you're supposed to do is
write the equilibrium expression. Yeah, put our expression up. I saw some of you guys already doing it, so that's good. That's nice to see. I'm just going to write that down here. So we got our products over reactants. And now we can set up our ice box. I'm going to make it move down a little bit here. Write ice. I rewrite my reaction. Give myself plenty of space. It's probably a little overkill this time for me, but whatever. I'd rather have too much than not enough. Okay, there are a couple of weird things going on in this problem. And we'll get at it as we fill this box in. So I'll let you guys finish up getting your box put together. Okay, let's start putting in what we know. What is our concentration of A? What can we put in there? The initial. And there's a little problem with it by putting just 0.4 in.
Oh wait, there's 2, so it's actually 0.2. Right?
Yeah, exactly. He caught this. We have 0.4 moles in 2 liters, but we want it in molarity, which is concentration. So we have to take our moles and divide it by 2 liters. So really we have 0.20 molarity of A. So watch that. It has to be in molarity. What else do we know initially?
1.5 moles of C. Wait. It's actually...
Yeah, it's actually 0.75, yeah. Yeah, we have 0.75 moles of C. So another thing that's kind of different about this one, we're adding both reactant and product at the same time to start off with here. So how much B will we have initially? We don't know. So it's going to be 0. Yeah, we start out with no B initially. We've just added A and C. Yeah.
So when for an equilibrium, it says 0.40 from B. Do we divide that by 2 as well?
Yeah. We are also going to divide our B down here at equilibrium by 0.2 liters to get that as 0.20 molarity. Okay, so we got that info in. Next step is to draw our arrows. So this is where we have to kind of remember Le Chatelier's here. The first off the start, I always like to look at is
C goes up, right? Because
this is kind of a weird one. So we have 0B, right? So what's going to happen to its concentration? It's going to go up. It has nowhere to go but up. Oh yeah, good way to think of it. Since it's 0, there's nowhere to go but up. So what's going to happen to the C then?
go down.
It's going to go down. And if we're taking away C, what's it also going to turn into? A. It's also going to turn into A. So you have 0B. So because we need to establish equilibrium, C has to be consumed to produce A. So what's that? Since the B can only go up, we're also going to be producing A at the same time. So that, because C is made of A and B, if we start turning C into B, it's also producing A. So that's why that has to go up. Okay, so now we can start putting our X's in, right? Let's do this one first. What's this one going to be? Plus 1x. Yeah, plus 1x. It's going to change by a factor of x, and it's going up. What's this one going to be here? Plus 3x. Yeah, coefficient. And then this one over here? Minus 2x. So now we've got a box here that we can solve for x in. We got 0 plus 1x equal to 0.2 molarity. Yeah, x is 0.2. And then we can start figuring out these guys. 0.75 minus 2x. And you get 0.35. And over here, we've got 0.20 molarity plus 3x. And that gets us 0.8.
Does it say equal to E?
Yeah, I just put it equal to E. It's giving us that equilibrium concentration. You don't have to put that on there. And the last thing we got to do now, we've got all of our equilibrium concentrations. Now we can finally plug our numbers into the equilibrium expression that we wrote up above here. So 0.5335 squared over 0.8 cubed times 0.20. Ooh, I'm being bad and I put my units in here. Let's see what you guys get. Do a total check here. Did you guys get 1.2? If you did that, then that's what it is. And then last question, product or reactant favored? Yep, it's still product favored.
So if it's less than one, it's reactant favored?
That's right.
Okay.
This is still a product favored one. Just barely. Just a tiny bit product favored. 1.2. So this stuff is basically, it's almost going to be equally favorable reactant or product. So not too much going on here. Okay, what kind of questions do you guys have right now? So the hardest part is actually the arrow designation, I think, here. I think really that is the toughest part. Would you guys agree with that?
Yeah.
Okay, so yeah, that's the part that. So just try to think back to Le Chatelier's principle, putting those in, and like who said the comment about if it's 0, it's got nowhere to go but up. Okay, Andy. Yeah, thank you with that one. Yeah, if it's 0, you know that one has to go up. It's got nowhere to go but up, so that's gonna be an up arrow for sure. That's right. That's right. So what you guys have to do for the rest of the time here, worksheet 2, there's 2 problems left to do it, numbers 4 and 7. 4 and 7 you can do now. Those are the ones that use ice boxes. Okay, you guys can get to it.